Okay, so I want to talk to you a little bit about regression analysis and matrix algebra. This is what we're going to be doing on the project, and I'm going to also talk to you a little bit about some stuff that's not in here, which is the efficient frontier and what we're going to plot out. I'll show you when we get there. Okay, so I wanted to talk to you a little bit about regression analysis because you're going to use regression analysis to calculate a beta on your stocks, each of your 5 stocks plus your portfolio, which you're going to form. And I will tell you about that later. All this stuff I don't really want to go into a major amount of detail on right now. We're going to come back and talk about it after you've actually done it. The dependent variable is the value that we want to forecast, and we're not exactly necessarily forecasting. We could just be trying to explain. So there are 2 reasons for regression analysis commonly, and one is to explain stuff, some random variable, and then the other is to try to forecast it. So we're doing this to calculate a beta. The independent variables can include any of these things, and I'm not going to go into great detail on that right now. The simple linear regression model looks like this. And when you calculate it using Excel, you're going to get an equation that looks like this. And so this is going to be, and this is the way we denote it when it's actually an estimated equation. This is more formal. This is what we're estimating when we actually run our regression. So I'll use this. And here, your dependent variable is going to be return on the stock. The independent variable, as I'm going to explain in the project, is going to be return on the market, and B1 is going to be your estimate of beta for the stock. Then B0 is alpha for the stock, and that's the intercept. So what you're doing is estimating a straight line. Sometimes a straight line isn't the right way to estimate, but this is your beta, the slope of the line. This is return on the market. This is return on security J, and this is your intercept, which is alpha in this example. Okay, so I'm not going to go into a great deal on least squares estimates. We're going to talk about that a little bit more when we do our wrap-up. I'm going to tell you that this is where you'll find your R-squared, which tells you the goodness of fit for the model. So how well does the independent variable explain the dependent variable? So how well does Rm explain Rj? And your coefficient is here. That's where you're going to find your beta. And then your intercept is here. But we're not going to concern ourselves with the intercept really. So here's a scatter diagram of the data that I'm plotting for this example, and this is the fitted regression equation. R squared, this is just telling you where we get R squared, and it tells you the goodness of fit. So let me go back for a minute and show you. This means that 88% of the variation in the dependent variables is explained by the linear relationship between the independent variable and the dependent variable. Some assumptions about the model, we'll talk about that later. So how are we going to test for significance? We're going to look at the t-test in particular, and we're not going to do too much of that because when we calculate beta, we don't usually really talk about the t-test and goodness of fit. But we're going to take a quick look at that. So we're going to, for that, we're going to use this equation. Excel will spit that out for you, and here's your t-statistic, which indicates that the regression coefficient is significantly different from 0. How do we know that? Because we compare it to usually somewhere around 2. It's really like something like 1.96. But to see if we can reject the null hypothesis at the 95% level that, I don't know how to do that, so I'll do this, that beta is equal to 0. So the null hypothesis is that beta is equal to 0, and we're going to reject the null hypothesis at the 95% level if we can conclude that the t-statistic is bigger than, the calculated t is bigger than the critical t of 1.96. This one is big enough that my guess is it would be at the 99% level that we reject that null hypothesis. So that's what we're doing. We can use the f-test to test it for significance of the model itself. There are a few little things about that. If you want to know more about it, you need to take econometrics. Because we're not going to cover it in this class. You might have had statistics, but the f-statistic isn't the best statistics. It's hard to find a really good goodness of fit statistic for regression. Anyway, that's another story. So we're going to reject the null hypothesis that beta is equal to 0, but if we do that, we're not necessarily concluding that the relationship is causal. So we're not necessarily concluding that X causes Y. Just pointing that out. So here's some more stuff on that. Okay, we're also going to use matrix algebra, and in your, I'm going to bring up a blank presentation to show you that what I want to show you, which is in your 3318 class, you told me that you calculated the standard deviation of the portfolio as equal to the weight of S, that was stocks, times this squared times the variance of S, plus the weight of bonds squared times the variance of bonds, plus 2 times the weight of S times the weight of B times the standard deviation of S times the standard deviation of B times the correlation coefficient between S and B, sorry, that should be an S, and you take the square root of that to get the standard deviation, and that's what you told me you did in 18. So, given that you know this, I can also tell you that there's a quicker way, sort of, to do this, and that's that you take the weight matrix and you multiply it by the variance-covariance matrix. So this is the variance of S, this is the variance of B, and this whole piece right here is the correlation of the covariance between S and B. This is the covariance between S and B. So this is the covariance matrix, and in this case it would look just like this. Here's the variance of S, here's the variance of B, and here's the covariance of S and B on the off diagonal. So you're going to see that. You're going to see that when you do your project. Okay, so we're going to multiply the weight matrix by sigma, the covariance matrix. That's this, and then we're going to multiply it by the weight again, so that's square. The only trick is, because we're going to use matrix algebra, we're going to have to transpose this first weight matrix in order to be able to do the algebra. Okay, so let's go back to this slide. So I don't know if you've ever had matrix algebra before, but just in case you haven't, let me just remind you a little bit about some of the terminology. First of all, you have an element, which is a single item in a matrix. So this is an element. And a matrix is a regular array of numbers arranged in rows and columns. So the way that we define this is m rows by n columns. This one is allowing for more than 4, but in this case it would be 4 rows by 3 columns. So this one would be a 4 by 3 matrix. But generally we designate by a matrix by its order, which we call the number of rows times by the number of columns. So we're going to do matrix algebra on this. This is an example. This is a 4 by 3 matrix A. some more definitions. A special matrix is a single value, in other words, a matrix with one value, is a scalar, and then you've got a row vector and a column vector. A transpose of the matrix is when the rows and columns are interchanged. So this is called a transpose. We turn this 4 by 3 into a 3 by 4. So just like I showed you before on this other thing, we're going to transpose the weight matrix in order to do matrix multiplication, which we haven't gotten to yet. Okay, so that's denoted as a prime. To do matrix multiplication, the number of columns in the first matrix has to be equal to the number of rows in the second matrix. So these two inside numbers have to be the same. And the result matrix will be a matrix of order m by, we're calling it q. So the outside two numbers will be the order of the result matrix. This will be a 1 by 3. So matrix C is going to be A11 times B11 plus A12 times B21. So this is the way we do it. We do these and we flip them and we do them multiplied by these and add them together. Then we take these and we multiply them by these and we add them together. And then we take these and we multiply them by these and we add them together. So C13 is equal to A11 times B13 plus A12 times B23. We're not going to have to do that because Excel is going to do it for us. So in 3318 we said that, in 12 as well, you discussed the fact that the weighted average, that the portfolio return is the weighted average of the returns of the securities in the portfolio. So this should say all I. And if we think of the weights and returns as vectors, we've got one little problem. W is a 4 by 1 vector and R by 1 is a 4 by 1 vector. They're both column vectors and those middle numbers don't match. You need these two numbers to match. So we're going to transpose the weight matrix, and that way we have a 1 by 4 and a 4 by 1. And the result is a 1 by 1, which is going to be the portfolio return, which is also a scalar. So you're going to get one number, it's going to be the portfolio return. For the variance, this is funny looking, but it's the same as that two security portfolio variance that you studied in 3318. Okay, so for an insecurity portfolio, it can get pretty complex when you're doing this using this formula. So we use matrix algebra to do this. Okay, and in matrix notation, it becomes W prime sigma W. And so we're going to take that transpose matrix, multiply it by the sigma matrix, and then multiply it again by the weight matrix. So we're going to do a 1 by 4 times a 4 by 4, and what result matrix will be a 1 by 4, which we're going to then multiply by a 4 by 1, and we'll get a 1 by 1 matrix. Okay, so that's what we're going to do. Alright, so let me show you a little bit more on the efficient frontier. So what we're going to do is we're going to draw the efficient frontier, which you also discussed in 3318, and it's where we plot the portfolio standard deviation against the expected return on the portfolio. That looks like a B, but it's an R. And we're going to see that it's going to look something like that, because when we combine any two assets in a portfolio, we're not going to get a straight line in that combination unless the correlation coefficient between those two assets is equal to a perfect positive 1. If it's anything else, anything less than perfect positive 1, then we're going to have that line where we combine. And I will do a follow-up video where we'll talk about that in a little more detail.